Technical introduction. My name is Taiga Hiroka. In this talk, I talk about the meta-complexity characterization of quantum cryptography. This talk is based on these two concurrent works. The first one is written by Bruno, Eli, Matthew, and Peter. The second one is written by me and Tomoyuki Moremae. Both results are same, so I will give a same in the one talk, in the single talk. First, as a background, I will explain one-way function. One-way function is a necessary assumption for classical cryptography. One-way function is a function f which can be computed f of x from x easily, but hard to invert x from f of x. We can construct several useful cryptographic primitives from one-way function. On the other hand, for constructing these primitives, one-way function is necessary assumption. In this sense, one-way function is necessary assumption for classical cryptographic primitive. Given this characterization, one natural question is to ask about quantum case. In other words, is one-way function also necessary for quantum cryptography or not? Recently, many works study this question and show the possibility of quantum cryptography without one-way function. First, as such a candidate, pseudo-random state generator was introduced. This primitive can be seen as a natural quantum extension of PRG, where a quantum algorithm outputs a pure state indistinguishable from her random states. We can construct this primitive from one-way function. On the other hand, the other direction is an open question, and in fact, there exists a black box separation between them. The other kind of quantum cryptographic primitive without one-way function is quantum cryptography with classical communication. In this type of quantum cryptographic primitive, we suppose that each party has a quantum computer, but communication between them are classical bit string. So example is quantum SKE with classical communications. We can construct this kind of quantum cryptographic primitive from one-way function, but the other direction is an open question. In fact, there exists a black box separation. So currently, there are many candidates of quantum cryptographic primitive without one-way function. So given this situation, it is natural to ask which primitive is a necessary assumption for these primitives. Although there are several candidates, one natural candidate is known as one-way puzzle. In fact, for constructing almost all of quantum cryptographic primitives whose outputs are pure states, one-way puzzle is necessary assumption. Furthermore, for constructing almost all of quantum cryptographic primitives with classical communication, one-way puzzle is necessary assumption. So in this sense, one-way puzzle can be seen as one of the necessary assumptions for quantum cryptographic primitive. Let me explain the definition of one-way puzzle. In short, one-way puzzle is one of the natural quantum analog of one-way function. So one-way puzzle consists of two algorithms, the sampling algorithm and verification algorithm. The sampling algorithm is a quantum polynomial time algorithm that outputs a pair of puzzle and answer. Here, these are classical bit strings. The verification algorithm is an inefficient algorithm that takes puzzle and answer as input and outputs 1 or 0. The correctness guarantees that the input of verification algorithm is generated by the sampling algorithm. Then the verification algorithm outputs 1 with high probability. So this roughly means that sampling algorithm correctly generates a good pair of puzzle and answer. The security guarantees that given only puzzle, no quantum polynomial time adversary can find answer star such that this verification algorithm outputs 1. So this is the definition of one-way puzzle. So this primitive can be seen as a natural quantum analog of one-way function because we can efficiently generate a good pair, but hard to find a good answer given puzzle. So somehow this can be seen as a natural quantum analog of one-way function. So given that one-way puzzle is a natural quantum analog of one-way function and necessary for almost all of quantum cryptographic primitive, we would like to construct this primitive from milder assumption. Currently, it is known that the existence of one-way puzzle implies that BQP is not equal to PP. So it seems extremely challenging to construct one-way puzzle unconditionally. So instead of try to constructing one-way puzzle, it is natural to try to construct one-way puzzle from that BQP is not equal to PP. So currently, no one succeeded in proving this open question in quantum cryptography. So we would like to solve this question. Furthermore, this question is also important for quantum advantage as well. This is because, as shown by Morimaya, Shirakawa, and Yamakawa, the existence of a one-way puzzle implies that one-way function or sampling-based quantum advantage. This means that if we can construct one-way puzzle without one-way function, which implies sampling-based quantum advantage. So as long as one-way function cannot be constructed from BQP is not equal to PP, if we show this open question, we have sampling-based quantum advantage. So this question is also important for quantum advantage as well. Because of these two backgrounds, I want to show this open question. But unfortunately, this seems quite a challenge because this question can be seen as a natural quantum extension, quantum analog of constructing one-way function from BQP is not equal to NP. This question has been a long-standing open question in the field of classical cryptography. No one succeeded in proving this conjecture. And in fact, there are several proof technique limitations for showing this open question. So that's one of the reasons why this is an open question. So because of this, it seems also challenging to show this open question. Despite of this background, recently, as an emerging paradigm to solve this open question, meta-complexity gains attention in the field of classical computational complexity. So roughly speaking, meta-complexity is a research subject that studies the complexity of problems to ask for complexity. So let me explain the recent progress about meta-complexity briefly. The first reason why we should care about meta-complexity is that sometimes we can overcome proof technique limitations. So in the classical computer science, showing the average case hardness of NP from the worst case hardness of NP is a long-standing open question, and this is also necessary for showing one-way function from NP is not equal to P. So although this is a still open question, recently a partial progress shown by Hirahara. He shows that instead of assuming this conjecture, we can obtain average case hardness of NP. Crucially, this statement is in itself completely unrelated to meta-complexity, but the statement is about interesting. Furthermore, it is considered that we need to overcome limitation of black box reduction to show this kind of result. But he shows that how to overcome this barrier by using the technique of meta-complexity. And there are several other results whose statements are completely unrelated to meta-complexity, but the techniques depends on meta-complexity, and it seems to overcome the proof technique limitation. That's the first reason why classical people care about meta-complexity. And the second reason is that in order to show this result, it is necessary and sufficient to show the worst case to average case reduction within meta-complexity. So it is shown that one-way function is equivalent to several average case hardness of meta-complexity problems. So this result is in itself interesting, but we can also show that P is not equal to NP can be also characterized by several worst case hardness of meta-complexity problems. So given these two characterizations, in order to show this conjecture, it is necessary and sufficient to show this direction. So because of these backgrounds, meta-complexity gains attention. So ultimately, we would like to obtain quantum analog of these plenty of results. So as a first step, I ask the following open question. So can we give a meta-complexity characterization of quantum cryptographic primitive? So this is a quite a natural question. And in our work, we show the affirmative answer and give a first characterization of quantum cryptographic primitive by meta-complexity. So this is the result. So let me explain it in more detail. In our work, we show that one-way puzzle is equivalent to quantum average hardness of gap K problem. So one-way puzzle is a natural quantum extension of one-way function. And the quantum average hardness of gap K problem is, roughly speaking, estimating Kolmogorov complexity of a given bit string is hard on average over a quantum algorithm. Okay, let me explain this definition in more detail. For this, I will explain the notion of Kolmogorov complexity. The Kolmogorov complexity is defined for each classical bit string. Kolmogorov complexity of a bit string X is defined as a minimum length of program that prints x. For example, let me consider the bit string x1 and x2. If the bit string x1 is a bit string that repeats 0 for many times, then it is sufficient to write a program which says repeats 0 for x1 times. So this program can be described by order log x1 bit strings. So chromograph complexity of such a bit string becomes small. On the other hand, bit string x2 is a random, and there is no way to compress these bit strings. We need to include every information into a program. So chromograph complexity of an uncompressible bit strings becomes large. In this way, chromograph complexity captures information which is contained in each classical bit string in a very clever way. In our work, we study the computational complexity of estimating this complexity value. So this is somehow meta-complexity problem. So in our work, as I said before, we show that one-way puzzle is equivalent to quantum average case hardness of gap K problem. This is the assumption that there exists some quantum polynomial time algorithm Q which generates a classical bit string X. And we require that given X, it is hard to decide whether the chromograph complexity of a given bit string X is large or small by any quantum algorithm. This is the assumption which we call quantum average case hardness of gap K problem. In this way, we give a first characterization of quantum cryptographic primitive by meta-complexity. Note that this result can be seen as a natural quantum extension of the following characterization of one-way function. In the classical case, it is known that one-way function can be characterized by classical average case hardness of gap K problem. Here, the difference is that they just consider a PPT algorithm instead of a QPT algorithm. So our result can be a natural quantum extension of the IRS-22 results. So from now, let me explain the technical details. So given that our result can be a natural quantum extension of IRS-22, one might wonder whether our results can be obtained by straightforward adaptation of their technique. Actually, it is no, and we need to introduce novel idea. So from now, I will explain it. For this, let me recall the IRS-22 approach. First, I will explain the easier direction, so showing the hardness from cryptographic primitive. In the IRS-22 approach, they first consider PRG, which can be constructed from one-way function. And then from PRG, they show classical average hardness of gap K problem. Here, the important observation is that classical bit string generated by uniform distribution has a large chromograph complexity. On the other hand, the output of PRG trivially has small chromograph complexity because PRG expands random bit string into a larger bit strings. So output of PRG trivially has small chromograph complexity. Because of this observation, this direction follows. So we also consider quantum case. So we also consider quantum average hardness of gap K and one-way puzzle. Fortunately, we have a 1/quantum analog of PRG, which we call quantum PRG. So the definition is slightly different from standard PRG. In particular, this algorithm does not have a random seed. Instead of that, we require that it must be statistically far from uniform distribution, but computationally indistinguishable from uniform distribution. We can construct a non-uniform variant of QPRG from one-way puzzle. Here, non-uniform means that a quantum algorithm takes advice as an input. And we also show this direction. But importantly, the same approach does not work in this setting because in particular, this algorithm does not have a random seed. So we need to introduce a new idea. But actually, this direction is easy direction. So I want to explain the difficult part in more detail. So I skip this part. So for showing the other direction, they consider average case hardness of estimating classical probability distribution. So this is the assumption that there exists some classical polynomial time algorithm C such that it is hard to estimate this value within multiplicative error on average over C. So I mean, there exists some algorithm C that this algorithm outputs x on average over this distribution. Estimating this value is hard. This is an assumption. We can obtain this assumption from classical average hardness of gap K problem by using the technique of Kolmogorov complexity. And as shown by Impagliazzo and Levin in 1919, one-way function can be obtained by average case hardness of estimating classical probability distribution. So it is natural to think about quantum case. And we also consider average case hardness of estimating quantum probability distribution. Fortunately, similar to IRS-22, we can obtain this direction. But actually, the most challenging part is to show this direction. In particular, in the classical case, for obtaining one-way function from average case hardness of estimating classical probability, they use a fact that a classical algorithm has a random seed. On the other hand, in the quantum case, we don't have a random seed, so we need to overcome that difficulty. Note that there exists a concurrent work by Krana and Thomas, which obtains a similar result for showing this direction. So let me explain the outline of this direction. For this, first I will explain IL-90 approach. So in their work, they show how to obtain one function from this hardness assumption. Actually, in their paper, they show the contraposition of this statement. So they show that assuming the non-existence of one function, then we can estimate this value within multiplicative error on average over any PPT algorithm. So the idea is as follows. The first observation is that this value can be estimated by counting the number of randomness R such that x is equal to CR. Okay? So the second important observation is that by using the famous Stockmeyer's argument, by querying to NP oracle, this number can be estimated by considering x as an instance and R as a witness. So in the Impagliazzo and Levin work, if we consider average case estimation instead of the worst case estimation, then actually NP oracle can replace with the non-existence of one function. In this way, they show how to estimate this value within multiplicative error. But this technique heavily relies on classical algorithm has a random seed. So the first observation is broken down if we want to apply this technique into the quantum setting. So we introduce other idea. So let me explain it from now. So instead of showing one-way puzzle directly, we first consider distributional one-way puzzle, which roughly says hardness of inverting conditional QPT algorithm. We can construct one-way puzzle from distributional one-way puzzle. So the remaining thing is to show this direction. Okay. Then we also show the contraposition of this direction. So we consider the non-existence of distributional one-way puzzle, and then we show that we can estimate this value within multiplicative error. So the first observation is that if there does not exist distributional one-way puzzle, then for each classical bit string B, we can estimate this value within additive error. This is the first observation. Let me explain the intuition of this. For this, let me explain the definition of distributional one-way puzzle. So distributional one-way puzzle is an assumption that there exists some quantum polynomial time algorithm Q that outputs X and B. This is the informal definition. X and B, and X is sent to the adversary. The task of adversary is to simulate the distribution of B. Condition on that, the algorithm Q outputs X. So this is the assumption. This is the assumption of distribution of one-way puzzle. So if there does not exist distribution of one-way puzzle in our world, this roughly means that we can simulate any conditional QPT algorithm. So by using this, it seems possible to simulate this value, right? By running this adversary many times. So that's an intuition why first observation follows. And the second observation is that we can decompose this probability into each these terms. Okay? So by the first observation, we can estimate each term within additive error efficiently. But the final goal is to estimate this value within multiplicative error. As a final observation, if we consider average case estimation instead of worst case estimation, actually additive error estimation of each term is sufficient to compute this value. So by combining these observations, we show that assuming the non-existence of distribution of one-way puzzle implies that we can estimate this value on average over any quantum polynomial time algorithm. So in this way, we show that one-way puzzle is equivalent to quantum average case hardness of gap K problem. So this is a result. So let me explain the future direction. So in our work, we show that one-way puzzle is equivalent to quantum average case hardness of gap K problem. So the natural direction is to think about other quantum cryptographic primitive. In quantum cryptography, other than one-way puzzle, there are many of quantum cryptographic primitives. So I want to understand why these primitives are so different by establishing the characterization of quantum cryptographic primitive by metacomplexity. By doing so, I want to understand why each primitive are so different. And the second direction is to think about the characterization of computational complexity by metacomplexity. In the quantum case, in the classical case, we also have a similar results. So we can show that P is not equal to NP can be characterized by several worst case hardness of metacomplexity problems. So we would like to show quantum analog of these results. And the third direction is to think about the characterization of several quantum advantage. In the field of quantum advantage, there are several distinct notions of quantum advantage, like proof of quantumness, or BQP is not equal to BPP, or sampling-based quantum advantage, or search-based quantum advantage. So I'd like to give a characterization of each notion by metacomplexity. So that's one future direction. So that's it. Thank you for listening.
Questions? Go ahead, sir.
Can you just go back a couple of slides? You say average case hardness of
This one?
yeah, is that over X? Your average over X.
For some quantum algorithm Q, this algorithm outputs X. On average, over the algorithm of Q, estimating this value within multiplicative error is half. This is the assumption.
Go ahead.
Sorry, related. Can you estimate that the added error is by repeatedly applying to
So what do you mean? You ask the third observation?
Yeah, why
Very roughly speaking, if each term is very small, then such an event does not occur on average over this algorithm, right? That's the intuition.
you mean the added error for each of the terms and we multiply it out?
Yes.
I see. Yeah, so I presume that the classical case one-way puzzles are the weaker and one-way.
Yes. The reason is that I forgot the reason. I forgot the reason. But one function is equivalent to one puzzle in the classical case. I mean, if the sampling algorithm is if the sampling algorithm is a PPT algorithm instead of QPT algorithm, then even if this algorithm is inefficient, this is equivalent to one-way function. So here by non-uniform, I mean, the QPT algorithm takes as an input log length of advice. So yeah, classical advice. So this is very similar to imbalanced QEFID. QEFI, EFI.
Any more questions? Yeah, go ahead.
There's one more shell code that is not equal and is equivalent to a meta question. They're analogous thing for like post one, so P not equal to or it's anything not equal to PQ.
Personally, I would like to show that three open questions to me. The first one is QCMA is not equal to BQP. I want to characterize it by meta complexity. The second one is QMA, and the third one is PP. If we consider NP, I guess it is not so difficult. I'm not sure.
Okay, let's thank the speaker then. Thank you, sir.